Mercury is weird. Within our solar system, each of the planets have their own special quirks. From Uranus' insane axial tilt, to the Earth's large moon, to Venus' her runaway greenhouse effect. Each planet is truly unique and an interesting treat to study for astronomers. Today, I want to talk to you a bit about why Mercury, the smallest of our Sun's planet, is unique, with a particular focus on its orbit and rotation, and what we can learn from it. The answers might surprise you, so get comfortable and let's dive in. Mercury's orbit seems a little strange at first glance. Not simply because it's the closest of the planets to our Sun, but it also holds the most eccentric orbit of all the planets. According to Kepler's first law, all orbits are an ellipse and not a perfect circle. No planet makes this more apparent than Mercury. In astrophysics, we express how much an orbit deviates from a circle in eccentricity. A value of 0 would be a perfect circle, and the more it increases, the more elliptical the orbit gets. And if the value goes above 1, the orbit becomes hyperbolic. For all of the planets in our solar system other than Mercury, we have eccentricities that are values below 0.1. Not Mercury though, who orbits the Sun on a wonky 1.2, giving it over twice that of the next most elliptical planet, that of Mars at 0.09. This means that its distance to the Sun ranges from 46 to 70 million kilometers depending on its position in its orbit. Mercury's orbit is also very tilted, which means the orbital plane is lifted, something called orbital inclination in astrophysics. Mercury's orbit holds the highest inclination of all the planets, which is also unusual. For a long time it was thought that Mercury's close proximity to the Sun had resulted in the planet becoming tidally locked, similar to as how the Moon is to Earth, meaning that the same side would always face the Sun. As our studies of the planet advanced though, we found out this is not the case, and the orbital and rotation periods do not match. Orbiting the Sun every 88 days and rotating its own axis every 59 days. Huh? Turns out if you divide these, you come to find out they're almost perfectly 2 to 3, putting the planet in a spin-orbit resonance, which is a much more interesting kind of lock than previously suspected. What this means is that in its orbit the planet rotates once for every third of its path, so that by the time it fully completes one orbit, the exact opposite side of the planet will face the Sun, as it did in that point last year. That means between sunrise and sunset on Mercury, an entire year passes. And another year will pass before the Sun will rise again. It turns out this is a perfectly stable way to tidally lock the orbit and rotation of a planet, and I would argue even more interesting than a regular tidal lock. Now that's already pretty interesting, but hold on, it gets even weirder. Due to its eccentric orbit, its speed is larger when it's closer to the Sun than when it's further away. And what this means is that at its closest approach, its orbital velocity will exceed its rotational velocity. If you were an observer standing in the right spot on Mercury as it made its closest approach to the Sun, you would see it rise, gradually slow down, stop, then reverse a bit, and set again before rising and returning to its normal path 4 days later. While this orbit may seem wonky, is it actually that strange of an orbit? We live in an age of exoplanets now, so perhaps looking at some of them for reference against Mercury will reveal more about its orbit. As of 2025, over 5,000 extrasolar planets are known, the majority of which turn out to have significantly higher eccentricities than the planets in our solar system. Now most of these are single planets, which you would sort of expect to have higher eccentricities, but even among extrasolar multiple planetary systems, none seem to resemble the solar system's orbits. What we can deduce from this is that it's actually the solar system that's unusual, with its near-circular orbits. As a matter of fact, most exoplanets with circularish orbits are very close to their star, which is completely the opposite of what we see in our solar system, where Mercury has the most eccentric orbit, despite being the most inward. I mean, what's going on here? Why is it doing that wonky orbit? When a planet rotates, contrary to popular belief, this is not a frictionless process. Over long geologic periods, tidal effects from the Sun and other planets create tidal friction, slowing the rotation of a planet. Among others, this is why the Earth's rotation is slowing. A similar process carried to completion on Mercury. Tidal friction gradually slowing the planet's rotation until it reached a 2 to 3 resonance. The way this works is that tides resonate with simple multiples. Once Mercury settled in this 2 to 3 ratio, the tidal force has stopped slowing its rotation, and things have been perfectly stable since. This at least explains why Mercury rotation is so strange, but tidal friction alone can't fully explain its eccentric and inclined orbit. Let's attempt to explain its inclination first. There are actually a few different ways to measure orbital inclination. You can measure in regard to the Earth's orbit, which admittedly is not the most useful since the Earth's orbit itself is tilted, but a better way to measure it is against the Sun's equator. But even this isn't perfect since the Sun's axis of rotation is also offset. Now if this confuses you, you're not alone, because how on earth would you measure the Sun's actual tilt? Like, what reference would you even use? You can't measure against orbit as that creates a paradox, but measuring against the Milky Way's plane is also not very useful. So instead we refer to the common angular momentum of the solar system's planets, through the solar system's center of mass. This creates an imaginary plane that we call the invariable plane, which, granted, is a lot more complicated, but provides the reference plane we need to measure the best inclination. Measured against it, we can sort of see a pattern where the inclination of planets is roughly inversely proportional to their mass. Now, this isn't absolute, but mass does seem to be the biggest factor here. But why are orbits inclined in the first place? The answer has to do with how planetary systems form. As I alluded to in my planetary video, the process by which the solar system formed remains at best partially understood. And the more we learn about exoplanetary systems, the less typical the solar system seems to be. But some processes we can assume to be near universal. One of those being that the most massive planet forms first. When this planet forms, it draws the most mass, therefore assuming the least inclined orbit. The less mass a young planet is able to gather, the more it will struggle to set in a not inclined orbit. And Mercury, being the least massive of all the planets, with the highest inclination, seems to confirm this theory. So that then brings us to the high eccentricity. Like I said before, Mercury has very little mass, which makes it very susceptible to the gravitational influences from the other planets. It is assumed Mercury formed in a much less eccentric orbit than it has today, which was gradually distorted over time by the influences from Venus and Jupiter to become increasingly eccentric. There exists a class of exoplanet known as eccentric Jovians. These are gas giant planets of mass similar to Jupiter in highly eccentric orbits around their stars. These planets can get flung well inwards of Mercury's orbit and then outwards to that of Mars. Such a massive planet in such an eccentric orbit typically spells doom for any other stable orbits in this system. Thus, almost all eccentric Jovians found are the only planets in their system. It is thought that eccentric planets destabilize their neighbors, and conversely having a lot of other planets around has a stabilizing effect on the orbits. This is due to the fact that energy exchanged between the planets during their revolution is usually concentrated on a specific body. Fortunately for the inner solar system, Jupiter has a very low eccentricity, so its distortion effects are only slight, Mercury being the least massive, taking the bulk of them. They are slight, but they are there. And thus, over time, we can expect Mercury's eccentricity to increase more and more. In 2009, a team of researchers decided to simulate Mercury's orbit over the next few billion years. They ran their simulation a few thousand times, and across their simulations found that more than 1% chance of Mercury's orbit being destabilized to such an extent it could fall into the Sun, or be ejected from the solar system entirely. In some simulations, it even ended up colliding into Venus and destabilizing the orbits of Earth and Mars. The only variable changed across these simulations was Mercury's distance to the Sun, by less than a millimeter each time. Not only does this reveal Mercury's orbit to be a lot less stable than it would seem, but it also hints at a major problem in Newtonian physics, something referred to as the n-body problem. While we can, with near total accuracy, mathematically predict the orbits of a two-body system, the math increases exponentially when there are more bodies introduced, to the point there will always be a large factor of uncertainty. The solar system, with its 8 planets and numerous smaller bodies, being a perfect example of a system that's ultimately weird, wonky, and unpredictable on large timescales, especially with Mercury. The large amount of additional bodies in orbit influencing each other in ways that are difficult to predict accurately over large timescales. That said though, we can be reasonably confident in the enduring orbital stability of Mercury for at least the next few 100 million years. In conclusion, Mercury has a weird orbit and rotation. It's tilted, eccentric, and sometimes its day goes backwards. And the reasons as to why are myriad and complex. From being the least massive and most influenceable of the planets to being bullied by Jupiter's massive gravitational field, the planet has settled into a truly one-of-a-kind orbit, one of the most unique and interesting ones found in the solar system. And all of that without even mentioning the perihelion precession, which I bet some of you thought was going to be this video's actual topic. Well, that's a whole separate rabbit hole. This video was sort of a deep dive into Mercury's orbit following a comment made on my Discord. I ended up learning a lot about our innermost planet, and I'm looking forward to applying this knowledge in my next Project Espa video. With this planet studied, I'm ready to move on to the next chapter for the world building series. So if that's something that sounds interesting to you, stick around and subscribe. This has been YiGi Online, and as always, thank you for watching, and I'll see you in the next one.